Hey,
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 everybody else here?
sure.
we're here.
Awesome.
But the bell's ringing at Banner
And they're
Fly.
here too. They're here on YouTube and Facebook too. Yay!
Hey.
Only took us 6 years to get this far.
Here we are.
All right. Well, good evening, everybody, and welcome back to our Sunday night offering of Astronomy Edutainment, the Sunday Night Astronomy Show.
Hey.
Ah,
First of all, I'd like to welcome back our two regular co-hosts for this evening, Mr. Paul Owen from the Moonshadow Observatory in beautiful Hampton. Paul, hey, good night.
Hello,
Good
hello.
evening. And Mr. Mike Powell from the PFO Observatory here in St. John. Mike,
hey,
hey. Okay, on tonight's episode of the Sunday Night Astronomy Show. Now, when we're underneath the night sky, it is easy to think that everything that we see is two-dimensional. Ancient Greeks and later astronomers believed stars were all roughly the same distance from Earth. Even after the Copernican revolution suggested that the sun was not at the center of the universe. Now, it wasn't until 1838 until Friedrich Bessel made the first successful measurement of a star's distance. Now, we hear astronomers often suggest about distances to stars in space or other objects, but how do we calculate the distance to stars, galaxies, and other deep sky objects? Tonight we invite Kurt Nason, our local astronomer extraordinaire, back to the program to help us understand this cosmic stepladder. Welcome back, Kurt.
hi, Ron. Great to be here. Oh, no,
Yep, serious Kurt.
All
All right, also tonight, Mike's going to bring back his binocular target of the week. That's it, as far as we'll go. Paul's going to deliver another. You Paul? Okay, yeah.
I'm
Cool.
here. I'm here.
Take a bad one, or are you okay?
Yeah, I fell. I'm not doing well.
All right. Paul's going to deliver another interesting Rosanna's fun fact. I'll have
Not
you
yet.
of your wonderful photo submission to share too. I didn't do too much of a what's up because it's kind of a boring week. Well, it's going to be cloud rain for us anyway. So sit back, everybody, and enjoy. And remember, this is a family-friendly, live, interactive broadcast. So let's get started then with a look at the cosmic stepladder. Mr. Nason, off to you, sir.
it's an earthquake. Okay, stellar distance. How far was that star? So as Chris mentioned at the beginning there, the ancient Greeks and right up until the mid-16th century or even later, they thought the planets were and the sun and the moon are orbiting around the Earth at the center of the universe, and the crystal spheres, and there's a crystal sphere for the stars on the outside of them, up there in heaven. And it wasn't until like in the with Galileo and Tycho and them, especially with the introduction of the telescope, you start to see a lot more stars out there. Then they got away from this idea and get wondering, well, just how far away are those stars? When you see so many of them like that, and a lot of dim ones, so they assume those ones are much farther away. So the method they came up with was parallax, which uses trigonometry that was known back in second or third century BCE. The Greeks devised that. So essentially, so if you're looking at a close star, and you know there's some stars farther away, if you pick one out you think is closer, and if you look at it, say from a different, pretend that's the Earth for a minute, looking at different areas on the Earth, quite far apart, and see if you could see that star shifting a little bit relative to other stars from each place. To get an idea for that, what you usually do is hold your thumb out, arm's length like this, right? And then one by one, close the eye, close the other eye, close one eye, close the other eye. You keep doing that, and you can see your thumb jumping back and forth. Right now, if you say looking at the wall like that, and you can sort of mark a spot on the wall where you're seeing your thumb each time, and if you can measure the angle from, say, between your eyes to those 2 points, and then measure the distance between your eyes, you can tell how long your arm is, or how far your thumb was from your eyes. And I know you can just measure the length of your arm, but they don't make yardsticks that go out to the stars, so there had to be a different way. And they tried that. They started trying to determine the distance around even 1500s, 1600s, starting back then. but they didn't have, first of all, they were trying to do it in different parts of the Earth, and that baseline wasn't nearly wide enough to get an angle on that. And sometimes it's difficult to pick out, which star to use. They assumed that the brighter stars were going to be closer. Right, so by doing that, if you had a wide enough base, so eventually they figured out, well, let's do it on from here. So at some time, but 6 months later, do it again. So you've got this very wide baseline here, which is 2 astronomical units. The astronomical unit is the average distance of the Earth from the sun, and it's roughly 150 million kilometers, just a bit less. So you got a baseline here of about 300 million kilometers, and that should be enough to make you see that star look different compared to the background stars 6 months apart. And so you can go with that. Problem was with some of the back in the 1700s, they didn't have any equipment good enough to resolve the stars that way. So they could not measure that particular angle. And there's a great book on this, Parallax, by Alan Hirschfeld. It's about 25 years old. And it's like History of Astronomy. That's an excellent book. It's one of the best books I've read on astronomy. All right, so when they do that, here's, you're measuring it from one side to the other. And so you see from here, you're seeing this here star here against the distant stars in this position. 6 months later from here, you're seeing this one relative to that star. So what they do, you've got that angle in there. What you do, they take the half of that angle. So you're going from the sun to there and taking out to here, and here's your angle in between these 2 points here. And so then they're taking half that one from there and using a little bit of trigonometry. And so you remember trigonometry from high school. You've got a right angle triangle in here. So you've got the baseline here, which is 1 astronomical unit. And you want to find, you've got your hypotenuse here. So the sine of this angle in here is this line here over the length of this line here. Right? So it's 1 astronomical unit over the distance that you want to measure, and that's in astronomical units. All right, so depending on how big that angle is, you're going to get a different number for the sine of that. Now, we assume that maybe the angle is equal to 1 arcsecond, which is 1/3600th of a degree. It's 60 arc minutes in a degree, 60 arc seconds in an arc minute. So assuming that was 1 arcsecond of an angle there, so you got the sine of 1/3600 gives you this 4.848 times 10 to the minus 6. Very, very tiny number. And actually the distance, you can turn this one around, distance would be 1 AU over that sine, 4.848, which would give you a distance of 206,264 astronomical units, which works out to 3.26 light years. And this becomes another measurement of distance for astronomers. They call it the parsec, from parallax second, right? So one parsec is 3.26 light years. So astronomers will tend to use either one of those. I always prefer the light years. It just seems more logical. Okay. So that's the calculation that goes into determining the distance. And even the nearest star, you could not get 1 microsecond of an angle there. Right? Even the shortest one, say to Proxima Centauri, it's going to be the smaller angle than that. Okay, so Frederick Bessel first measured parallax, coming close. They were getting some answers, but in retrospect, they weren't very close. But Bessel came very close here to the known one for 61 Cygni. And here's Cygnus in here. This is where Paul lives. And in there, you come down this wing and up a bit. There's a blow up in here. There's a star. And just to the side of it, there's 61 Cygni. It's a nice double star. So give it a look in binoculars sometime. And he's able to measure the parallax of that one. And he came up with this decimal 314 arc seconds, which worked out to 10.3 light years. And we know the distance now is 11.4. So we've got better measurements of it. So that's reasonably close, everything about 10%. And shortly after that, Struve and Henderson were also doing this and coming very close. And they got similar accuracy on Struve did it on Vega, which is about 25 light years away. And Henderson did it on Alpha Centauri, which is about 4.3 light years away. You know, the longer the baseline you get, you're going to have more accuracy. You're going to be able to measure those smaller angles. So they're doing it nicely there with 6 months apart from Earth. And now with satellites up there, you get even a wider angle. So the Hipparcos satellite, when it was taking pictures of the sky, it could do parallax out to 1,600 light years. Hubble with its wide field camera number 3, an upgrade, it could get out to 20,000 light years. With Gaia, which has been up there and giving loads and loads of data for several years, it's you could get a resolution down to 1 microsecond. 1 microarc second would take you out to about 40,000 light years. So the Gaia can give you accurate distances out to about 40,000 light years using that parallax method. Now Fraunhofer, or Bessel here, was able to get a nice measurement like that because of Joseph Fraunhofer. Was an excellent optician, and he was one that started making excellent refractors. Right? And he's also the guy that came up with, developed the equatorial mount. But he developed a heliometer, and this is a telescope. You got the objective lens there, 2 of them, like that. There's a sort of split apart, and you get an image in both of them. And they were used for a heliometer, used to measure the width of the sun. So you could get an image in each of them. So moving this, so you get the 2 images overlapping, and then you start to move the movable one apart till the 2 edges are touching. And there's a micrometer measuring how far that goes, so they can measure that in their micrometer and then work it out from that to figure out how wide the sun was. But could you also use that for telling how far apart, say, binary stars are? And so Bessel used from one of the Fraunhofer heliometers to work out the angle between the star he's looking at and the stars relatively nearby and how that changed. All right, so that would take us out to about 40,000, right? And we got lots of star clusters in that area that you can use and find out. Beyond that 40,000, you've got some, say, globular star clusters. Many are less than that distance, but a lot more are farther out. But if you wanted to measure the distance to a galaxy, okay, so the parallax gives you the first line, say your first yardstick, but you need something else to take beyond that. All right, so we have Cepheid variables, but a couple of things to know about here with the stars. The brightness of the star depends on its luminosity. Right? That's the total amount of energy that's giving off. It depends on the radius of the star and the surface temperature of the star. So to get the luminosity, it's actually the square of the radius times the fourth power of the surface temperature in Kelvin. That'll give you the luminosity. And the distance also makes matter, because the farther away a star is, the dimmer it's going to get. Right? So stars are isotropic, which means they're giving off their light equally in all directions. And so you got a star in here. So if you're out in this area here, right, you're going to get to this cone of light in here. But if you move twice as far away, right, you're getting it twice as much light in this direction and twice as much light in that direction. Right. So if you go from, you're doubling your distance, you're getting your distance away, you're getting 1/4 of the light coming. It's going to be 4 times dimmer. You go out from like that again, say out to 3 times the distance, it's going to be 1/9 as bright. Go out to 100 times or 10 times, it'd be like 100 times dimmer, like that. So it's the inverse square. The farther away you are, relative distance, it dims by the square of that distance. So that's the inverse square law. It works for this. It also works for like measuring gamma rays, things like that, as long as you're not giving off from a point source. All right, so there's a term called absolute magnitude that they use. So this is for luminosity. And this is to put all the stars on an equal footing. Then have some stars that are intrinsically brighter, so that compares to, say, something like the sun. So you need to set it for a standard distance, and astronomers have picked that at 10 parsecs, which would be 32.6 light years. And pick that because at the time when they come up with that number, most of the bright stars, that'd be like the average distance for the brighter stars. So if we happen to move our sun from 150 million kilometers away out to 10 parsecs, its magnitude would drop from, what is it now, about minus 26, minus 27, it'd go to 4.83. Right, so if you can think of the constellation Draco, it's got those 4 stars in the head. Somebody's been looking at the sky, and the dimmest of those 4 stars is a very beautiful double star, Nu Draconis. And to the naked eye, Nu Draconis is approximately that same brightness there. So if you see that, that's how bright the sun would look at 10 parsecs, or 32.6 light years. All right, now there's a type of star called a Cepheid. These are yellow supergiants, and they're variable. And their brightness can change by several magnitudes over days or even months, depending, there are 2 different types of them. All right, so what's happening? These giant stars, when they become a red giant, they're pretty much at that temperature where you're back and forth between gravity and the fusion reaction wanting to blow the star apart. Usually it's quite stable. Like for the sun, it's fairly stable because it's in that area. But when you're getting up in a red giant from one of these yellow supergiants, it's very unstable and sort of almost like breathing in and out at a regular pace, like that. So when it's at its smallest like that, it's getting hotter and more pressure on the inside, which means the temperature in the core goes up, which means the fusion reaction goes on a lot more quickly. It's using up a lot more fuel at the time because it's hotter like that. And so that extra energy coming out is the photons coming out from that, bits of light. They will bounce off the helium atoms out there and ionize them completely, give the electrons of the helium atoms enough energy to break away from the helium nucleus. And so that gives you a lot of extra free electrons in that area. And photons just love to bounce off of electrons. So you've got a lot of free electrons out there. It's going to be scattering a lot of the photons that were going out and giving light. Therefore, that light's not getting out to where we are, and it's making the star look dimmer. So as it's hotter in the middle like that, and more electrons more atoms being ionized, a lot more electrons, and the star dims from somebody viewing from outside. Right, so as it's doing that, it's very hot, so it's also trying to blow the star out a bit. So this time the nuclear reactions are overcoming the force of gravity from the mass of the star. So as it's blowing out like that, it's getting cooler. Eventually, as it cools, it's going to reach a point where gravity becomes dominant again, and it starts to move back in, like that. So as it starts to move in, it starts to heat up again. Eventually, you get a point where the fusion reaction coming out from that takes over again. So the star's going out and in like that, and as it's moving out, it's getting brighter, and then it starts coming back in. It's getting dimmer, and it starts coming back in, and starts to brighten up again. Right, and for the Cepheids, it could be diameter changes by as much as 25%. Now, Delta Cephei. Here's Cepheus, badly shapen house here. Here's Delta. Now, in 1784, John Goodrich discovered that this is a variable star, watching it over time. Its magnitude changes by a bit, 3.48 to 4.37. The smaller number, of course, is brighter. You get really bright stars or bright planets, they're going to be on the negative numbers. All right, so you notice that this one's varying by that, like that, by every 5.37 days. All right, so this is a reasonably close Cepheid star. It's the second closest Cepheid. It's 887 light years away. All right, so that was within distance for being able to do parallax on that one. Back around when it was 100 years or more ago. Okay, so second brightest Cepheid. What do you think the brightest or the second closest? What do you think the closest one is? Give you a hint. It's on this map. It's also the most northern one. Polaris is the closest of the Cepheid stars, and it's about half the distance of Delta Cephei. Right. So we'll see Polaris again right here at the end of the show here, or the end of this one. Okay, so here's the light curve here for Cepheid, for Delta Cepheid. So it comes up bright, down, and back up again. All right, so Henrietta Leavitt, working at the Harvard College Observatory, and along with the other, what they call them, the Harvard computers. And they'll be getting, they will be taking about the Harvard telescope will be taking a lot of pictures on these glass plates that are about 8 by 10. And they also opened up a telescope in Peru at Arequipa. It was the largest telescope at the time, and they were doing the southern hemisphere like that from that. So all these glass plates are coming up to Harvard College, and the computers here, women would be looking at these, giving them each of the stars that they could see on these glass plates, and trying to determine the type of star it is based on spectrometer. So some of these were taken with spectrometer, and also determining the brightness of the star. And so Henrietta Leavitt was given the Magellanic Clouds to look at. All right, so she did this, found several hundreds of Cepheids in a small Magellanic Cloud, and noticed, in looking at the period of brightness to brightness like that, she realized that there's a relationship between how bright they got and the length of the period. And so we noticed that the brighter ones had a longer period, or a longer time from one brightness to the next brightness. Now this could be something useful. So the other thing you have to look at when you're looking at brightness of a star is the distance, as we saw. And so she assumed that they didn't know how far away the small Magellanic Cloud was, but she assumed they were far enough away that we could assume they're all the same distance, within this very small area. I don't know how wide the galaxy is, but most of the stars in there are compared to the Earth, that distance, they're all about the same distance from us. So in 1912, she took a bunch of those and verified this period luminosity relationship. The longer the period, the greater the brightness. So that was a regular thing. So if you could measure the period of that particular Cepheid, you'd know what the brightness was. And since these ones are all at the same distance, what they're measuring there for brightness would be actually the luminosity. Here's one of the glass plates. This one is, you can look at this one. This one's from the 40s. Here's the Andromeda Galaxy here. There's M110 and M32 in here. Now you see all the markings on here? So when they're looking at these, Leavitt had used a positive and a negative of the same field and put it over as sort of measuring the distance or the size of the stars one over the other. And you can tell if some have changed or not. So they're looking at that. There's a lot of things you have to take into account with different types of telescopes. There'll be some corrections you have to make for that. If anything away from the center, there'll be some corrections you have to do to that due to curvature. If there are any clouds or anything like that, light mist, that would be included with the data. You'd have to make an allowance for that and several other things. So there's a lot of work went into determining these things. And they went through thousands upon thousands of these plates. All right, so the known distance of Cepheids in the Milky Way. So they had some Cepheids that were within close enough to figure out through parallax how far away it is. And so if you can see one of those, you see what its period is, and look at one with the same period in the small Magellanic Cloud. Okay, if they got the same period, they're going to have the same luminosity. And so the difference in brightness from the one in the Magellanic Cloud would be due to distance. So by doing inverse from the inverse square law, they could tell how bright that star was, or how far that star was in this small Magellanic Cloud compared to the one here in the Milky Way. And so knowing they've got the same period, they know that the same brightness, and one in the cloud is dimmer only due to distance. So by working out with the inverse square law, they can tell how bright it actually is, or how far away it is, right? So that means we can go to a distant galaxy, and if you can get Cepheids in there, you can tell how far away that galaxy is. All right, so in the 20s, at Mount Wilson, Edwin Hubble he detected Cepheids at M31, and he used that to estimate its distance. And he verified it's another galaxy. There's arguments more or less going on between him and a couple others, and Harold Shapley. And Shapley thought the entire universe is out to about 300 light years, or 300,000 light years. And other people were thinking, no, they're much bigger than that. And so by doing finding the variables there in M31, calculating the distance, it put the Andromeda galaxy much farther away than what they thought there was. So you realize that M31, or the Andromeda galaxy, is not part of our galaxy. It's another galaxy out there. And in the decade before that, Vestos Leifer at Lowell Observatory was using spectrometer, measure stars, measure galaxies, and finding the redshift. So the farther, if they're moving away from us, the lines here in the spectrum would be shifting toward the red. And using that, Hubble and Humason, they were determining how far away these galaxies are and how fast they're going away. We realize that the farther away the galaxy is, the faster it's moving from us, right? Some of these were moving toward us, like Andromeda galaxy, they have a blue shift moving toward us, but most of them are moving away from us. And they come up with this relationship that, it's a linear relationship. If it's twice as far away, it's moving away from us twice as fast. Right, so then they come up with Hubble's law from that. So they may be able to measure the distance of galaxies anywhere from 10 megaparsecs to a few hundred megaparsecs. So the more distant it was, the greater redshift and the faster the recession. All right, so they come up with the Hubble constant, which measured in kilometers per second per megaparsec. And before him, Georges Lemaitre, he had come up, he more or less proved the universe was actually expanding. There was this theory, and he had a lot of backing for it. But by doing this with the Hubble constant, it actually was the final proof in it that the universe is expanding. And suddenly the universe got a lot bigger than what they thought it had. All right, now, if we want to go beyond that, they're going to be so far away, galaxies so far away, you're not going to be able to see any Cepheid variables in that. So there's another way you can do it with these type 1 supernovae, with more or less stars about, up to maybe a couple times the mass of the sun. So you get two of them that are binary, and they're orbiting each other. The more massive one, the bigger one here, is going to go through its fuel a lot quicker. So it's going to be more massive. They are the shorter lifetime. So eventually, going around like that, this one's going to start to expand out into red giant, right? And that's going to get much, much bigger like this. And so eventually it's getting much closer to that. So these two are going to eventually start to share an atmosphere. And the radiation from the stars here are going to blow that away. Right? They're going to be orbiting around that, getting a little bit closer. And eventually this one is going to get a little bit bigger. And the big one here eventually becomes going to run out of its fuel and become a white dwarf. And the other one eventually is going to start to get bigger as well. So now you get the white dwarf and this other one, smaller one, the original smaller one, getting bigger and bigger like that. And so eventually it becomes a red giant, and the white dwarf here is drawing off a lot of the hydrogen from that. And the hydrogen builds up so much that there's a runaway nuclear explosion here, runaway fusion explosion, and blows that white dwarf to pieces. And it's going to be very, very bright. And it's brighter than the entire galaxy that it's in. There's usually nothing left over, and what was left of the other star gives it a big shove, and it goes pushed out of the way. All right, so they assume that these type 1a supernovae are going to have the same peak brightness because they all happen at about the same mass. The star white dwarf picks up 1.4 times the mass of the sun. That's the time when it's overcoming. It's going to get so much on there, so much mass, that the hydrogen on the outside is going to go have that runaway fusion reaction and just blow itself apart. So theoretically, it should have the same luminosity. And very, very distant galaxies. They can see that, measure the brightness of it, inverse square law, tell them how far away that very distant galaxy was. All right, so they started looking at the various type 1a supernovae going back at various distances. And you get far enough back, starting to compare them to the Hubble law, actually it's now the Hubble-Lermaitre law. There's a difference as you get back farther. And it seems that the supernovae are dimmer than they should be. And one of these things must be wrong. So it turns out that they realized from this that the universe is not only expanding, at some point it started increasing. All right. So this happened maybe 6 to 7 billion years ago. The acceleration of the expansion happened. And that Hubble Lermaitre constant is now around anywhere between 68 and 72 for a number. Right, maybe quick one here. Alternative methods other than the parallax and say the Cephians. With star clusters, you can assume the brightest stars in clusters are all roughly approximately the same brightness. Actually, if you know how close one is, and you get a more distant star cluster, and you see how bright those stars are compared to the one that you know is closer, and you know for the parallax how far away it is, you can estimate how bright the other ones are. They know how bright they are, but you can estimate how far away it is from the inverse square law. And you do the same with if there's too far away to maybe be able to measure the brightness of the stars, you just take the overall brightness and compare it to a closer one. Another one is red giant stars. And with these ones, something like about the size of the sun is going to become a red giant eventually. Right now, some of these are going to be not big enough, not massive enough to burn fusion. So you have sort of helium core, or burn helium. So you have a helium core, but fusion of hydrogen going on the outside, and they'll just go like that until maybe they'll collapse to white dwarf. But in some of them, every now and then, you can get a brief runaway explosion that just lasts a few minutes of the helium core suddenly getting hot enough to go through a fusion. And it's just like a fusion bomb. It only lasts for a few minutes. You get this helium flash, and where it's all roughly about the same mass where this happens, you can expect that the brightness of that flash to be about the same for any of these. So that's another one they can use for determining distance. And that's about the end of that, except for this thing about Polaris.
Wow.
How enlightening.
There we go. That was quick about Polaris.
Yep. Did you read it?
No, too
Okay.
Bring it
Well,
back.
you have two people walking up, looking at Polaris, and they're coming to the edge of the cliff, and they don't see it.
The end of the cliff or Polaris?
Oh,
Both at the end of it.
oh, geez.
So everybody's
Anyway,
out there, yeah,
It's
everybody's-
interesting you talk.
Sorry. I was going to say,
Everybody.
everybody that's online right now, they have to participate in the quiz here in about 2 minutes.
Okay.
So it's interesting you talk about the inverse square law because that's used in, well, I mean, it's all about
Photography,
light.
yeah.
It's but it's used a lot in photography.
Yeah.
Because when you're using flash photography and whatnot, it's you really got to know. You don't have to know the exact math of it, but you
Yeah.
have to know the principles of it, and it's all based on. As soon as you start talking about it, it's like, oh yeah, that's pretty
Yeah.
cool.
Yeah, same thing like working in a nuclear power plant. You had a pump there. If you do a gamma reading on it close to the pump, you can estimate how far, what the dose rate would be at maybe 10 feet or something like that. So you give you an idea of what the dose rates are going to be if you're going to be working in that area.
Yeah, you just have to know the light fall off and what the actual math of it is.
Yeah, as long as it's not a point source, and as long as it's like in a pump like that in a bowl, and it's going to be more of a everything going off in the same different directions there. So we can,
Yeah. Anyway, it's interesting how all of that stuff from back then used for what it was used for is used in so many other things. Because like you said, it's for a lot of people it's basic math, but a lot of people
Yeah.
don't understand that law. So
Yeah.
anyway, interesting.
I got a question, Kurt. So how would we calculate the distance to a planet? If a planet is, like if we got something like Saturn, it takes 30 years to go around the sun, and we're catching up to it every year, and it's in a different
Okay.
location. Orbits are
you're using
elliptical.
Kepler's laws. Kepler's law for that is third law. So that's the distance. There's a relationship between with these. It's the square of the distance and the cube of the period, or vice versa, like that. And so it works out that way. So if you know the relative distance of all the stars from this, or all the planets, and if you're able to know the exact distance of any one planet, then you could know how far away all the planets are. And they were coming up with some reasonable, very close numbers, but it wasn't until they started bouncing radar off Venus in the early 60s that they got an exact distance to there that gave us an exact distance to all the planets.
Well, that's like you were saying on the beginning of your talk about them coming up with a I'll say the word fictitious point, and then something about the star they created, or they didn't create.
Yeah, just imaginary star. Yeah.
Thank you, imaginary star, where they would look at that and consider, okay, if it was from that point, then from there on it
Yeah.
it
You can
worked.
take an actual measurement.
Yeah.
Okay, yeah, because they're all elliptical, right? I mean,
Yeah. So when they're using that relationship, it's the average distance of the planet.
okay, gotcha. All right, wow, that was a lot to cover.
Yeah.
And
Yeah.
well done. Okay, I think we're ready for binocular target of the week. Thank you, Kurt.
I know better.
Welcome.
Binocular target of the week this week with Idaho Bud. He like Jimmy Kimmel, he's back. Is the cosmic question mark.
Uh-oh.
No questions? Okay.
Another question?
It's a
Yes,
British
it's-
asterism in the shape of a question mark. It is visible through finerscopes, binoculars, small telescopes with all low magnification. There are 5 stars that form the Cetus head, 2 bright stars to the left hand side, and one halfway up between, you'll find the cosmic question mark. How would I find it in the sky? Well, at midnight, when it gets up a little higher, that orients itself at 120 degrees southeast, look up. You will see Taurus. You'll see Pleiades. You just come over off the long end of Taurus. The next one over is Cetus. You'll find the bright star here. Just follow it around, and the cosmic question mark is right in this area right here. You'll sweep across. You'll find it. It'll stand right out. Again, there's the head of Cetus, and look, there's the question mark. You can't tell me you don't see a question mark there. It stands right out there. What does that look like? It looks like a question mark. And here's a photograph I took of my backyard. There's Taurus, Pleiades, and look here, question mark. So it stands right out. Not a difficult target to find, not a difficult target to see. 10 by 50 binoculars, 1, 2, 3, 4, 5 bright stars, very, outstanding. It's not a problem to see. Once you come across it, you'll know you're there. Compared to the full moon, at least 3 full moons across. So a good sized target. Now you ready for this one? How do astronauts clean up? They use the vacuum of space.
Oh.
Yeah.
Oh.
Target of the
Yep.
week. The infamous Idaho
Yeah.
Bud. You notice he even got his own cup of coffee here. Look.
That sucks.
Yeah.
Yeah.
Oh man.
There you go.
Vacuum of space.
Mm. Okay. We'll take it. Got no choice. Thanks, Mike.
Oh,
Welcome.
Okay.
How you know what happened to Idaho Bud? He's
I don't know
back.
what happened.
yeah.
I was wondering. Okay. And so were others.
Dust myself off
They,
now.
they were getting worried. So yeah.
I don't have a vacuum of space here.
He's all polished up. Yep. A little bit brighter after that talk earlier.
Yeah. Okay, Mr. Owen. I'm going to
All
share
right.
us Rosanna's fun fact.
See if I can figure out this thing if it still works. Hang on. There. And this is this week's.
Rosanna's Fun Fact.
Well, welcome back, Rosanna. Sorry about last week. We missed your opening thing, but my computer is almost back to normal. So you're back, and we're happy to have you again. So let's get right into this one. So Rosanna writes, there we go. Hi, Paul. Life is full of surprises, although there is always an ebb and a flow of happenstances that capture one's eye, imagination of interest. This week, I have picked my 2 favorite surprises. Now, let me just get the photos up here. There we go. To start off, researchers have discovered a young protoplanet with a rather engaging name of Wispit 2b. Now, Wispit 2b, or not to be, she's funny, is embedded in a ring-shaped gap in a disk encircling a young star. While theorists have thought that planets likely exist in these gaps and possibly even create them, this is the first time that it's actually been observed. Now, the image of the Wispit 2 system was captured by the Magellan telescope in Chile and the Large Binocular Telescope in Arizona. The protoplanet Wispit 2b is a small purple dot to the right of a bright white ring of dust surrounding the system's star. A fainter white ring outside of Wispit 2b can be seen. Now, even if it's a protostate, Wispit 2b is a gas giant about 5 times as massive as Jupiter. And the massive protoplanet is just about 5 million years old, or almost 1,000 times younger than the Earth, and about 437 light years from the Earth. Now, let me see which way this is going to go. There we go. So, excuse me, being a giant and still growing baby planet, Wispit 2b is interesting to study on its own, but its location is this protoplanetary disk gap is even more fascinating. Protoplanetary disks are made of gas and dust that surround young stars and function as the birthplace for new planets. Within these disks, gaps of clearings in the dust and gas can form, appearing as empty rings. Scientists have long suggested that these growing planets are likely responsible for clearing the material in these gaps, pushing and scattering dusty disk-like material outwards and creating the ring gaps in the first place. Our own solar system was once just a protoplanetary disk, and it is possible that Jupiter and Saturn may have changed ring gaps like this in that disk many years ago. And now another little surprising story that crossed my path this week. Oh, what's the wrong way? There we go. Let's start back in February 1990 inside Mission Control at Cape Canaveral, while officials are watching a bank of monitors showing the space shuttle Atlantis blasting off. This is the National Reconnaissance Office, is the agency that operates America's spy satellites. And for the NRO, a high-stakes mission was on board Atlantis, a new state-of-the-art highly classified satellite named Misty. And there is Misty. Now, although everything about this satellite, excuse me, was a top-level secret, it is incredibly hard to launch a spy satellite in secret. The NRO officials knew that as soon as Misty was put out into orbit, the Soviets and amateur space watchers across the globe would be tracking its every move. So 8 months later, the same NRO officers gathered in the same control room to watch the monitors focused on Misty. With a nod, direction was given, and the screen showed that the multi-billion-dollar satellite exploding into a shower of debris. And so and that was Misty there, by the way. And then as it blew up, kaboom, and everybody cheered. Surprise! This was all according to plan. Fast forward 6.5 years to Boring Air Force Base in D.C. Anna Montez from the DIA, Defense Intelligence Agency, has recently had her security level raised and has been invited to a special meeting. At this meeting, an NRO officer explains the story of Misty, its deployment and then decoy explosion, as if it had malfunctioned. It was all a ruse. Misty originally gave off specific electronic signals, allowing the world to see it as an electronic communication satellite. Thus, every time it flew over Russia or other areas, those on the ground would block their communication systems until it had passed. Unbeknownst to most, the explosion masked a switch to stealth mode, and now Misty, still alive and well, was cloaked and have become a picture-taking satellite. You won't see it in this picture due to its cloaking abilities. Let me just get it. Here we go. Although it could still be found and tracked, one would have to know exactly what to look for. Not all surprises are the good ones. 10 days after September the 11th, 2001, Anna Montez was arrested. The FBI had discovered that she had been a spy for Cuba for 17 years, and shortly after that meeting in 1996, she had revealed Misty's massive advantages to the handlers in Cuba, knowing they could make a fortune selling the information to other countries. The multi-billion-dollar Misty program, including 2 other launches, had been compromised by Anna years before. And the final twist in this story, Anna's sister Lucy and Lucy's husband, plus Anna's brother Alberto and his wife, all were FBI agents. None of them had a clue that she was a spy. So Thanksgiving at that house must have been fun. So Anna, how's work? Can't talk. Is there pie? I hate you all. And that's this week's No Sound Rosanna's Fun Fact.
Wow.
Oh, there you go. That's what a fun story.
That's
Yeah.
different.
Mystery and intrigue for sure.
Isn't that wild, right?
Yeah.
So
they-
after
so
all
they-
that, she's a spy for 17 years, feeding another country with all this information. Isn't that wild?
So they send her the signal, and then they pretend that it exploded.
Well,
that
there
they
you
can-
go,
They
right?
could cloak it from there on. Wow.
But what a devious but yet ingenious plot
Yeah.
that they came up with, and because everybody knows this thing is coming around at a certain time, they automatically shut her down and they cloak themselves from it. Pretty smart.
Pretty smart.
Anyway, thanks, Rosanna.
Thank you, Rosanna. That was really interesting.
That was awesome.
All right, let's get to a few photos. And that's my part, I guess. So I'm gonna just put this to a transition scene for a second so I can open up my photos here for our audience and share my screen. And it'll be just gonna
The
guess,
screen.
share. We're still here, folks. Just gonna bring it back here now, I think.
There you go.
Yep. Okay. All right. So let's take a look at what we got. Now this one is from Joseph Ingalls, and I didn't get this picture up last week, and I promised I would get it up this week. So this is the one that I had actually as my cover photo for a little bit. Joseph says, my granddaughter Olivia took this photo with our Sea Star S50.
Oh,
Yeah,
for her.
our first look at the Comet Lemon. We like to go out and look at all the stars on clear nights. He says, here's my granddaughter Olivia's picture of the Comet Lemon taken from a gravel pit behind my house here on Graham and Ann. She's 13 years old and knows a lot about the stars. To be honest, I am her student.
Awesome.
He says,
Isn't
yeah.
that fantastic?
Says we use the Sea Star quite often now and are trying to learn how to use a recently acquired Meade ETX 125. Still learning how to get it lined up and what eyepieces to use. So I suggested that he go to YouTube and take a look there. But that's great to see. I mean, this is the thing about Sea Stars is that they're becoming a family instrument too, right? So
Yeah.
let me get this. I can get this on full screen, can I? Maybe I can't. Here we go. That's better. Okay. Thanks. So thank you, Joseph and Olivia. I'm going to switch now to Kim, and I'll pronounce it wrong, so I'm going to say Thalassoulis. Now Kim says, "Hey guys, sharing an image that I took on Saturday night from a dark sky site in southern Australia."
Wow.
Yeah, so a 25 or 30-second image captured with an ASCAR SQA55 imaging rig. And he has a site called skymaps.com if you want to have a look at this equipment. It shows Comet C 2025 R2 Swan near the Eagle Nebula. And the green color of the comet's coma contrasts beautifully with the pink color of the nebula.
Yeah, very
It
nice.
sure does, yeah.
Yeah. Yeah. Well, we got pillars of life there.
Yeah. Pillars of creation, yeah.
Or creation, yeah. I always say life. Same thing to me.
The same thing, yeah. Life creation.
Eagle
Great
Nebula.
shot.
Very nice.
There we go. Thanks, Kim. Okay, let's go from there to Deanna King's captures of the Milky Way. She said captured these in Keswick Ridge during October. And
Very
she
nice.
says, enjoy. So here's a few.
It's dark up there, yeah.
Oh yeah.
Yeah,
There you go. Beautiful.
nicely done,
Yeah.
Deanna,
Yeah. Nice nicely positioned between those trees.
I say, I love the trees.
for sure.
Yeah. Yeah.
All right, I'm going to flip over now to Brad Perry. And no, that's not Brad Perry. Yes, it is Brad Perry. Yes, it is.
Yeah, it's right.
I'm used to seeing a scenic one.
Yeah.
Yeah. He said, just sharing this capture of Comet Lemon that I got on Monday night before the clouds rolled in. He said this was taken about 50 kilometers north of Fredericton on a logging road in a Bortle 2 area. So I had virtually no light pollution or cars blinding me. He said, even then, I could only just faintly see the comet with the naked eye. It is a tough one for sure.
Yeah.
I got lucky and I caught the tail of it in my very first test shot. So I didn't have to spend a lot of time hunting around for it with my camera.
Yeah.
Oh,
So he used a Sony A6000 plus a Sigma 150 to 600 millimeter lens at 503.9 millimeter. Ioptron Skygutter Pro. This is a 40 by 30 seconds at f6.3 at ISO 1600. No calibrations frames, he says, and processed in Serial and Photoshop.
right on.
No, nice job.
Nice done, yeah. Looks great in photos for sure. Yeah, it doesn't.
Oh yeah. Yeah.
It's not even a neo eyes to me, but it's still.
Did you guys see it? Did you look at it in binoculars?
No.
Yeah,
No.
it's beautiful. I saw it last night. It's
Oh,
about 2 degrees long.
it's
Really,
just
yeah.
beautiful in binoculars.
I
had
caught it-
my-
I had it in my 8-inch Daub, or in my Daub last night, and it was nice in that.
Yeah.
Upside downy, but yeah, nice.
Yeah. Well, when I went and shot it that night, I had to find it first, so I was using binoculars, and it's just so nice. I rather enjoyed the view in the binoculars better than taking a picture of it.
Okay.
It was just
Well, that's
so
why
nice.
it was the Bino Bud target last week.
What's that?
That's why it was the Bino Bud target
Yeah,
last
yeah. No, it was nice. It's always nice to see it with your eye. Absolutely.
Okay, we're gonna go from there. Thanks, Brad. To Francois Theriaul's captures here.
Whoa.
Yeah, nice,
Yeah.
right?
He
That's
said, here's a
crazy.
couple of pictures I worked on this week. He said they are both reprocessing of images I captured in August-September of this year. I have had 2 weeks of solid cloud cover here in Moncton, so took the opportunity. This is a Wolf-Rayet star. The Wolf-Rayet star is at the center of the nebula. Turns out to be 5 times larger than our own sun and about 400,000 times as bright.
Wow.
What we see in the nebula is the bubble of gas being blown out by the intense radiation and the solar wind from the central star.
Crazy.
Wow. His telescope was an Astrotech AT8N Newtonian, focal length of 800 millimeters. Camera was a ZWO ASI 1600 millimeter Pro. Exposures, I won't get into all the detail on those, but the total was 13.8 hours of capture.
Yeah. Yeah. Well, nice work as usual.
Yeah.
Yeah. Very nice. Very
Just
nice.
incredible
It's nice
stuff.
to see the difference between the reflection nebula and the emission nebula
Mm.
shot. If that's what I'm assuming that's what it is. Now he's narrow band, so I'm assuming that's what we're seeing. Usually the blue designates oxygen.
He has H alpha at 58 times 300 seconds, oxygen 3 at 54 to 300 seconds, and S2 What's
Sulfur 2, yeah.
so yeah, sulfur 2.
Okay.
Yeah.
54 at 30 seconds or 300
Yeah.
seconds. So yeah,
Yeah. Really nice. Nice job.
nice job.
Beautiful job.
One more here from him. The Wizard
There you
Nebula
Wow.
Wizard.
for Halloween.
Yeah.
Now the NGC 7380 is an open star cluster, or open cluster, sorry, in Cepheus, which groups together 40 young stars. It is surrounded by an emission nebula, SH2-142, which is commonly called the Wizard Nebula. I try to come back to it every year around this time, because I find the target challenging, with the large bright core being surrounded by a relatively dark dust cloud. Its large nebula clouds are being pushed around by the hot young stars and the delicate pillars and Bach globules along the perimeter of the central cluster.
So he's upside down, eh? If you're trying to actually see the wizard.
Yeah, you're right.
Yeah, because
We're off to see the wizard.
his hands are on the top. If he was the other way, he's kind of sitting like this. His hands down like this. He's looking
Right.
down.
Well, it kind of looks to me like he's holding a flower in his hand and he's blowing it.
It's your imagination, eh? Whatever you want to
It
see.
is.
Whatever the clouds show you.
Yeah.
He
Yeah.
used a Malincam VRC8, focal length of 1625 millimeter. The camera again was a ZWO ASI 1600 millimeter Pro. Total capture time was 6.5 hours.
Yes, sir.
Yeah. Yeah.
It's
Very nice.
He does
Very
nice
good.
work. Man.
Yeah, incredible. Thank you, Francois. Keep them coming.
Yes, indeed.
Let's flip now to Robert Carson. Robert's capture said, hi Chris, this may be too late for the Sunday show, but here are my photos of the Comet Lemon and Swan. Took these October 23rd with the C-Star S50 with only AI denoise and brightness on the C-Star app. So there's Lemon and here's Swan, I guess.
Yeah.
So I'm there, yeah.
He's picking them up from the beach. No problem at all.
Yeah. He says tiny star trails were caused by the wind. So it does happen.
Good satellite.
Yeah.
Yeah. Nice job, Robert. And a couple of others that he had captured last night. He said, here are the pics I took last night at St. Tress Beach with you and Mike. He said, the Andromeda and the Triangulum galaxies.
Yes, sir.
They do a pretty good job.
Yeah.
And there's Andromeda. Of course,
There
sideways.
you go.
Yeah.
Yeah.
That's the
Just
star of the
fits in
show.
there.
Just fits, yeah. The star of the show this time of year.
Yeah.
Oh,
Awesome.
sure.
Thanks, Robert. All right, going to go from there to this one from Melissa Magpie. She says, hi, love your page. I just took this picture in Fredericton with my iPhone 16. I pointed it at Arcturus and circled the comet. So it's a circle in the other picture, but here's Corona Borealis and there's a comet right there. So yeah, so she did get it. So I'm getting a lot of images from people with smartphones that are sending them to me and saying, here, I got, is this it or am I in the right
Yeah.
spot? And Stellarium works really well for that. If you've got Stellarium mobile on your phone, hold your phone up and hold it around the sky and it'll show you. It'll draw the constellations for you. Free program. I've been finding it's very helpful for objects like this. So good job there, Melissa. I'm going to flip to Chris Benoit's capture here of the sun from the other day.
Still a lot of spots.
Still a lot of spots. Yeah. Kurt, you said that they get closer to the center as we get to maximum or after maximum, or
By the time they're getting very close to the center, that's when they flip. Polarity flips and they go away and then start over again, coming in again at about 35-degree latitude. So as it works on throughout the getting maximum and beyond, they're going closer and closer together.
maximum and beyond. Okay. Yeah.
Yeah.
So we are on the downside, huh?
Right, well, getting there.
Okay.
They don't know really until they can't tell at any one time. It's averaged over, say, 2 or 3 months, and
Okay.
you take it that way.
As long as it gives us more aurora. More aurora. We need more aurora.
That's what
Me
everybody
more.
wants.
That could
All
be
right.
a song.
Yeah.
Yeah.
Could be.
Could be a song. Why don't you go on ChatGPT, tell them to write a song about Need More Aurora. See what you get. That'd be fun.
And here's his capture of Comet Lemon as well. It's kind of neat because you're seeing these pictures all over social media of Lemon, and it's kind of like when we had the aurora and when we had the solar eclipse, and everybody has a picture up, right?
Yeah.
But it's great to see that so many people are capturing it. So
Well, that's the thing. They're getting out.
Well, the
That's it.
technology's there now. Like, you rewind 10 years ago,
Yeah.
and you wouldn't have seen near as much as you see now.
No.
And what you're seeing now is a far better level for most beginners than what some of the more advanced people would have been doing back in those days. So,
Exactly. Yeah.
yeah.
Here's David Smart's capture. Just got an opening set in the sky. This R2 Swan here.
Yep.
And C2025 Lemon here. So
Yeah.
A little tail on Swan, not much, but
yeah, it looks great. 3 minutes capture.
Really good.
it's beautiful.
Good
Was
stuff,
that
David.
tail is really visible though, isn't it?
Yeah.
Okay, going to go from there to Mark Fitkin's capture here. He said, just Galaxy Group and Aries. He said, Big Dog users take notice of this nice grouping for dark
nice.
sky observations. Also, Double Star fans should check out one Aretitas. Okay, we'll take it back up here. Look at this nice grouping.
That's a
Nice
galaxy
little
in there.
grouping.
A bunch of galaxies in there. Wow.
Notified here, so
Hmm.
yeah, pretty cool.
I wonder if that group has a name.
He
Galaxy-
says, Galaxy Group and Aries, he says. Image acquired locally in Bronte with C-Star S30, 4K and denoised, 60-second exposures in EQ mode, edited in Snapseed.
Hmm.
Mark's probably on here, so he might want to comment.
Yeah, maybe if you are Mark, just chime in to see if it is a group or not. Or a named group, I should say.
Yeah.
I'll check my
Okay,
book.
quickly over to Kathy Adams. Kathy's got
Oh,
the
very
capture of Pleiades.
Yeah, there's a nice ladies, hey?
Just showing it off to some people last night at the beach, and yeah, it's just amazing.
Yeah.
Seven Sisters are an open cluster of blue stars, therefore very hot, housed by the constellation of Taurus. Now, in mythology, the Pleiades are the seven daughters of Atlas and Pleione, and she's their dwarf 3, have about 5 hours of integration time over 3 nights. She says using 30-second exposures and a gain of 60. Love it. Yeah.
It's amazing, like I say, we know about everybody who's got those sea stars. If you can maximize your time and just leave it on one target for a longer period, the results. I mean, Kathy's showing what you can do because it's all about gathering photons. And the longer you have it out there, the more light you gather, the more detail you get. And this is perfect. Just proof of the pudding right there.
That's right.
She's using a dwarf, which is
She had dwarf 3, yeah.
Yeah.
Similar. Yeah.
Yep. Yep.
Very
Well,
nice.
actually, her dwarf 3 is a 35 millimeter
Yeah.
lens, whereas the dwarf, the 50, the C Star 50, I mean, is 50 mil. So, and I don't know about the focal length distance, but I think if the C Star users, if you could put more time into a target, I think you might get similar results what Kathy's getting. So,
Nice job, Kathy. As
Nice
always. This one
Yep.
comes from Jennifer LG. Nice Comet Lemon shot there.
oh, very nice little star right above it. Eh?
Was that Arcturus? No.
No, Arcturus was
she
below it.
Yeah, I don't know
That
which one that
depends on what it was taken.
She actually, I think she asked what it was, and I didn't see anybody comment on it yet. But
Yeah, right on.
Nobody made a comment yet.
What was it? What was the date?
Comment.
yet? Oh, wow.
Does she have a date? Does she have a date for that
It's
picture?
up on the Astro Imaging page. I think they're.
I think. I'd have to look it up. I think that was the star I was using the night I got mine, and Arcturus would have been down and more to the left.
Left, yeah.
Yeah, but if it was taken 2 weeks ago, Arcturus was the other direction of it. Because I got it on the other side.
Yeah. Did she say when she took it?
No,
No, I'll look
she,
it up.
she might have. Yeah, I've only grabbed the one photo of her images there. So.
Okay.
Great job, though, Jennifer.
Anyway, nice. Yeah, beautiful.
And
It's nice,
clouds.
it's nice when you get other objects in the
Absolutely.
field of view with it, right?
Like I said, you can see the clouds there too, and she got it through the clouds. That's awesome.
Yeah.
Yeah.
Okay, well, there you go. So we love getting your images. As you can see, we love sharing them too. So you can send your images into astronomybythebay@gmail.com. Please send them to that address, not to my Facebook page, because I get them on email through the 3 different email addresses. You have my Facebook page and now this one. So I'd rather get them everything to go to astronomybythebay@gmail.com. There I can see them all in one spot and make sure that I don't miss any. And we'll have them up on our next broadcast. So thank you.
Oh, Mark said that's known as the NGC 678 group.
678. Okay.
Okay. Thank you, Bart.
Okay. We have October, November calendar here.
November. Oh,
I know.
Oh, Chris, before you
Yep.
get into that,
Yep.
can I
Please.
just
I'm looking
show
for
this-
something, so you go ahead.
I just want to show this book. I don't know. We're kind of squished down in the corner, but
Here, I can probably highlight you maybe. Can I?
yeah.
Oh,
Wait,
I gotta stop
well,
sharing. I have to stop sharing first.
okay. Yeah, just stop sharing. I'll be big
Yeah,
enough.
yeah.
Mark says it's a correction, Paul. It's NGC 691.
Okay. This book here is called The 100 Best Astrophotography Targets, and it's been out for quite a long time, and it's based on by month, whatever's up in the sky. So for those who have like the sea stars and the dwarfs and all that stuff, if you want to have something that's a really nice book guide that you can even learn stuff about, this is from the Patrick Moore series of books. And if you ever watch Backyard Astro, Trevor Jones, this is a book he used when he first started his channel, and I still use this book today because this stuff doesn't change. It's it goes on until infinity unless something blows up. But in any event, it gives you the 100 best targets every month. It explains to you where they are in the sky, their names. It's designed for astrophotography. So if you're shooting it with a telescope, it'll tell you, how many frames of how many this and that. But if you just want to use it for a book to reference with your sea star or your dwarf, and then down the road, if you ever decide you want to step into the, a little bit more complex rig, then this book is still even better for that kind of stuff. So it's kind of a book that you can start with and you can progress along your astrophotography journey with. And it's something you can have for years and years and years, and you'll get lots of enjoyment out of it. Anyway,
Awesome.
so you can show that.
Thanks, Paul.
Okay.
I'm just going to quickly go back to my slides here because I just wanted to make sure that I pointed out the last two. And it was this one, I think. Should be there, I guess. Yeah, so our October, November calendar. Let me get back to our people. Here we are. Our October, November calendar here by Kurt puts out this calendar every I think it's 6 weeks, Kurt, eh?
Monthly. I make it just before the St. John Astronomy Club meetings.
Now, there's not a whole lot happening this week. I mean, a couple of transits, egresses, I guess. First quarter moon comes up on Wednesday. St. John Astronomy Club meeting at 7 o'clock on Saturday. Following week, we're having our event at the Irving Nature Park, hopefully here on November the 8th. That's posted on my Facebook page. But anyway, you can get the calendar yourself at sjastronomy.ca. Just download it right from there. And I'm going to flip to Lisa's look up calendar. This is her calendar for October. I know she's going to owe me one here for November very soon. Lisa puts together this great calendar. She lists the event here on the left-hand side, the date of the event, the peak time for the event, and what you need to see it with, naked eye, binoculars, or a telescope. You can find Lisa at Ruby Moonbeams on Instagram, Mastodon, Facebook, Threads, and now on Blue Sky. And I'm going to stop sharing for a second. I'll let you guys talk amongst yourselves for a moment while I get our closing thing ready to go.
Oh,
Go ahead. So talk amongst yourselves.
Yeah. I'm talking to myself actually. So how was it? It was actually quite good. But you know what? I didn't like, what was it you didn't like? I'm not.
Okay, so speaking of T Corbor, there's guys projected by looking at 3 or 4 other times that it's gone, shot up in brightness. And he realized that they seem to happen about the same time in its period. And one of those periods happened back in March or April, and didn't happen then. But the next one occurs, within a couple of weeks of November 10th. So it might be time to start watching for T Corbor to go kaboom again.
Oh, really? Okay.
Over the next few weeks.
Awesome.
This would be that one peak time to do it.
Still waiting
It might happen, it might not.
Still waiting for the blaze star with a comet beside it.
Yeah. It'll be out of the way by then.
Oh, true, but
Yeah. You got a really
Awesome.
white field to do.
Yeah. Okay, everybody. So in closing tonight, thank you all for joining us again this evening. Kurt, thanks so much for joining us. Really appreciate it.
Thanks.
Hope to have you back again soon.
Checks in the mail, I hope.
You're
waiting,
gonna-
waiting,
we are going to mention that next week we're going to be talking about accessories, right, guys? Just maybe what you need to have for accessories, what you should be considering for accessories. And here we are at the time of year that you might be wanting to ask for a few of these accessories from
Yeah.
from Santa. So we'll be talking all about accessories next week. So special thanks again goes out to Rosanna for her continued contributions to our program. Paul and Mike, thank you guys for all that you do for the program. Also, remember too, we do love getting your photos, so send them in to astronomybythebay@gmail.com, and we'll be happy to put them up in our next broadcast. And if you have a suggestion for a topic for future shows, we always like the topics. Let us know, because we want to talk about what you want us to hear about. Please let us know at the same address, and please let your friends and family know too that we will be back here next Sunday night at 8 p.m. on YouTube and Facebook to entertain you or edutain you on astronomy and the wonders of the night sky. So for now, then, from Mike, Paul, Rosanna, Kurt, and I wish you a very safe and happy week. Safe and happy Halloween, everybody. Kurt, let's have a look at your shirt there. I got a rock, I'll be.
I got a rock.
You probably do.
Hey, that was an asteroid shirt. Right?
Oh, okay.
That's just spooktacular.
Yeah, okay. We're leaving on that note. Everybody, so open your eyes to view the skies and keep your scopes pointed up. Good night, everybody. Thanks for joining us.
Night.